thank you for this invitation. I am Paul Brunet, and today I'd like to talk to you about some recent work we've been doing with concurrent Kleene algebras. And so I'll start with a historical perspective on concurrent Kleene algebra. So it's a fairly recent model. It was introduced in 2009 by Tony Hoare and some collaborators. In 2011, they added more detail to the model. In particular, they studied various instances of the model and the relationship between concurrent Kleene algebra and separation logic. But initially, CKA was presented in an axiomatic form, and so the question of what was the free concurrent Kleene algebra was left open. And a first step towards this was achieved in 2014 when Georg, Struth, and Michael Lawrence showed a completeness theorem. So they exhibited a free algebra for a very related formalism. And I'm going to give you more details in a moment, but just to give you an idea of the sort of time frame that this stuff happened. And the same year, another paper was published actually in the same conference, adding tests to concurrent Kleene algebra, thus showing, and this was the first step towards using concurrent Kleene algebra as a program verification framework. But there were some mistakes in this paper about CKA with tests. So a second paper was published 2 years later, fixing some of those mistakes. Then in 2017, we showed that CKA was decidable and actually X-space complete. The next year, we showed the completeness theorem for CKA, so an equivalence between an axiomatic presentation and a semantic presentation. And what I really want to talk about today is these 3 papers that we published last year, adding something related to tests, actually observations, to be able to turn this into a more effective verification framework, and also adding boxes to deal with other aspects. So the starting point of all of this is the theory of Kleene algebra, which can be presented as the algebra of regular expressions or regular languages. So this framework uses the syntax of regular expressions. So you have constants 0 and 1, you have letters from the alphabet, you can concatenate expression, you can sum expression, and you can take the Kleene star. And very naturally, you interpret those as regular languages. So for any such expression, you can compute a set of words that is denoted by this expression, which we call the regular language denoted by the expression, and we can compute automata for these languages, and we can algorithmically compare automata. So I gave you a very small example here, but I think you might be familiar with these things. Perhaps slightly less familiar is the axiomatic presentation of Kleene algebra. You can also list those axioms. You don't actually need to read all of them. It's fairly standard stuff. The sum is associative, commutative, and idempotent, that sort of thing. But you have a fairly small number of axioms that capture exactly the identity of the equivalence of 2 expressions with respect to their regular language interpretation. So 2 expressions are provably equal if and only if they denote the same language. And what does that have to do with program verification? Well, you can modify this formalism slightly to get what is called Kleene algebra with tests, which can be thought of as the algebra of imperative programs. And you have almost the same syntax. You have regular expressions with 0, 1, letters from an alphabet A of actions. You have also concatenation, sum, and Kleene star, but you have a new construction here that allows you to, here, you can't see my, sorry.
We can see your pointer.
You can see my pointer?
Yes.
Okay. So you have this construction here. This construction that allows you to add a Boolean test in the syntax of regular expressions. So, and these Boolean tests are built from a finite set of atomic tests and then constant zero, true and false, conjunction, disjunction, negation. And with this, you can encode a while language. If then else will be encoded as the sum, so non-deterministic choice between either asserting that the guard condition holds and then executing else, and then executing the then branch, or asserting the negation of the guard condition and then executing the else branch. Similarly, you can do a while loop by non-deterministically looping, and in each time you enter the body of the loop, so inside the Kleene star, you assert the guard condition and then execute the body. And when you leave the loop, you check that the condition no longer holds. So with that sort of interpretation, zero can be thought of as an abort program that kills the execution. One is a skip program. Then your alphabet A consists of atomic actions. You have your tests. Concatenation becomes sequential composition of programs. Sum or union becomes non-deterministic choice, and the star is a non-deterministic loop. And you interpret those as languages of guarded strings. So a guarded string is an alternating sequence of states. So a state is a valuation of each of the atomic tests. You say that for each test, is it true or false? Then you perform an action, then you reach a new state, etc. State, action, etc. And you can also give an axiomatic presentation of this algebra. So using the axioms of Kleene algebra, the axioms of Boolean algebra, and interestingly, these four axioms, which are often omitted because usually they use a different syntax for Kleene algebra with tests, but in my syntax, you need to add these four axioms, which say that the disjunction is actually the sum, the conjunction is actually the sequence, and the constant true is 1, and the constant false is 0. So asserting false is the same as aborting, asserting true is the same as skipping, and asserting a conjunction is the same as checking both arguments, and checking disjunction is the same as being able to check at least one of the two arguments. And so with these axioms, you can again prove a completeness theorem. This is very nice because this logic, Kleene algebra with test, it subsumes Hoare logic, propositional Hoare logic, in that you can express a Hoare triple. So precondition B, program P, postcondition C. This holds if and only if, and I'm going to skip to the last of these equivalent presentations. This is equivalent to stating that you can, if you assert the precondition, execute the program, and then assert the negation of the precondition, of the postcondition, then you get no behavior at all. This program is equal to 0 because there are no possible execution that, starting from a state satisfying the precondition, after executing the program, ends up in a state that does not satisfy the postcondition. So what I'm going to talk about today basically is, can we do the same for concurrent programs? And first I'm going to present concurrent Kleene algebra. Some of you may be familiar with it already, but I think at least to convey my notations, it's important that I present this bit. And then I'm going to talk about adding observations or partial observations to CKA, and then I'll talk about boxes and mutual exclusion. So a first step towards concurrent Kleene algebra is bi-Kleene algebra. So we take Kleene algebra and we add to it a parallel product and a parallel iteration. And to axiomatize it, we say that if we forget about the parallel operators, we get a Kleene algebra. And if we forget about the sequential operators, the sequential product here and the Kleene star here, so we only keep 0, 1, the parallel and the parallel iteration, this is a commutative Kleene algebra because parallel composition is commutative. Now, we can list these axioms. This is well defined, but what is the free bi-Kleene algebra? What is the semantics that corresponds exactly to those axioms? And the answer is, instead of considering languages of words, we're going to consider languages of Palmsets, which can be thought of as concurrent traces. So if you think about words as being totally ordered finite sets with labels corresponding to the letter in each position, then a Palmset is the same thing, except the order is no longer total, it's partial. So formally, a Palmset is given by a finite set of events, a partial order of these events, and a labeling function that associates to each event some letter from our alphabet, or if you think about this being a trace of a program, some atomic action that was executed, or some observation that was made at this event. And we consider those up to isomorphism. So when I write Palmsets in my slides, I'm going to forget about the name of the events, only drawing the labels and the ordering. Then we can combine Palmsets. So we have, for each letter of the alphabet, we can build an atomic Palmset that has just one event carrying that letter. Then we have the empty Palmset with no event at all. And if we have two Palmsets, P1 and P2, we can compose them in sequence, putting every event in P1, every event in P2, all of the order in P1 and all of the order in P2. And we also add that every event in P1 happens before each event in P2. So we add links between the events of P1 and those of P2. And we can also compose P1 and P2 in parallel, putting them side by side and adding no links at all. With this, it's very easy to define semantics for our bi-Kleene algebra expressions. So everything happens like for regular languages, except now when we have a parallel composition, we take the semantics of E parallel F is the set of Palmsets we can build by taking a Palmset from E, a Palmset in F, and putting them side by side in parallel. And similarly for the parallel iteration, we just take finitely many Palmsets from E and put them side by side. And the result I mentioned earlier in 2014, Mike Lawrence and Georg Struth showed that indeed this is the free semantics for the axioms of bi-Kleene algebra. But at this point, this is not really concurrent, right? Because when you have two things that are in parallel, they stay in parallel forever. They can't interact. So to add some concurrency to the model, we use this axiom called the Interchange Law that is reflected in the semantics by the subsumption order between Palmsets. So we say that a Palmset is subsumed by another one. So P is subsumed by Q if intuitively P is more sequential than Q. So what does this mean? Formally, it means that we have a map from the events of Q, the big Palmset, to the events of P, the small Palmset, This map must be a bijection, meaning we don't create any events or delete any events. This map should preserve labels. An action A should be mapped, an event labeled with A should be mapped to an event labeled with A as well. And it preserves the order. So every ordered pair in the big one is sent to an ordered pair in the small one. But the small one is allowed to have more ordering. And you can think about this also as a relation between an implementation and a specification. The specification tells you which are the necessary dependencies, but the implementation is allowed to add more dependencies. Maybe you specified your algorithm to run on 2 parallel machines, but you need to execute it in a single machine, so you find some interleaving that still preserves those dependencies that were necessary. And we can now define concurrent Kleene algebra as a weak biclinear algebra, so we forget about the parallel iteration. And it must, but we keep all of the axioms that do not mention this operator, and we add this new axiom, the interchange law. It's also called sometimes the weak exchange law. And so in 2017, we showed that to test whether 2 given expressions denote the same language up to subsumption, this problem is decidable and X-space complete. And to do that, we basically used an inductive construction to build automaton, but we modify it to build Petri nets. And then we developed an algorithm to compare those Petri nets for language containment up to subsumption. And then the next year, with different collaborators, we showed that indeed this semantics matches this axiomatization. So two programs are provably equal if and only if they are semantically equivalent. So this is very nice. And so when we had these results, we thought, well, now we can actually use this to do program verification. And there was this idea that was already around about using concurrent Kleene algebra with tests. Since to do verification with Kleene algebra, you add tests, so you add a Boolean subalgebra inside a Kleene algebra. Well, you can do the same thing and add a Boolean subalgebra inside CKA. Unfortunately, with just this specification of what is concurrent Kleene algebra with test, you can do the following derivation. You take any test T, any program P, and you write the program assert T, execute P, assert the negation of T. Using the CKA axioms, you can rewrite. You can say, you can see that this program is smaller than that one. Then you convert this sequence into a conjunction, and then T and not T, this is false, and asserting false is 0, and 0 in parallel of anything is 0. And so this means that if you remember the whole triple encoding we had earlier, this means that any program is any test is invariant under any program, meaning this is not useful at all for program verification. So we had to leave this idea of concurrent Kleene algebra with test, but wanted to find still something CKA based to do verification. And so if we look at this counter example, we can try and see the ingredients that make it work and see if there's something we can blame. And there's only one choice here, because the CKA axioms, we want to keep them. The Boolean axioms, we want to keep them as well. And the fact that asserting false is 0 is also fairly reasonable. So the only thing that doesn't work, that is suspicious, is that conjunction and sequence are the same thing. And indeed, this works in a sequential world, where if we know that if we checked immediately after checking A, we check B, then A and B must hold at the same time. But in a concurrent world, between the assertion of A and the assertion of B, somebody else in the concurrent environment might have modified the memory state. And so it's possible to observe A and immediately after observe B, and not doing those two observations on the same state. And so our fix was to replace this identity, conjunction equals sequence, by an inequality. A particular case of sequence is conjunction. And so then the syntax and the axiomatization follows very easily. We take the syntax of concurrent Kleene algebra. We add this new construct to add Boolean tests, which are built as Boolean expression of a finite set of generators of atomic observations. And then we take the axioms of CKA, the axioms of Boolean algebra, and 3 glue axioms. So the fact that disjunction is the same as non-deterministic choice is still very reasonable. To check a disjunction, it's the same as guessing which argument holds and then checking that one. I discussed on the previous slide that the fact that conjunction is smaller than sequence, and also this is a fairly reasonable thing to add, that asserting false about the program. And because we have this, we remove the identity between conjunction and sequence, we thought it was also a good idea to remove the identity, to not identify true and skip, although this is debatable and it doesn't change much technically. So then we need a semantics, a model for this algebra. And so we, similarly, as we had for Kleene algebra with tests, we here consider Palmsets over 2 sorted alphabets somehow. So events are labeled either with an action or with a state. So a valuation of every atomic test to true and false. And subsumption was defined by having a map. So here, subsumption in this model is also defined with the existence of a map, such that if you restrict it to the actions, so these A, B, C, Ds, it should, the condition is the same as for the ordinary subsumption. So the map should be bijective, preserve labels, and preserve the order. For states, however, it's almost the same. So the map should be surjective. It should preserve labels. It should preserve the ordering. But now it's allowed to identify different states. So different events that are labeled with the same state. So here you can see that you have on the right-hand side, you have twice this 110 state. And both of these are mapped to the same one in the small Palmset. And this is the same intuition I explained earlier, is that it is possible that these 2 observations were made on the same state. However, you can't do it the other way around, because you can't split a state into 2 different states. And we showed that indeed the axioms I showed on the previous slide and the semantics I show on this slide match. And a small technical interlude. To prove this, we developed a framework called Concurrent Kleene Algebra with Hypotheses, inspired by some work by people in Lyon on Kleene Algebra with Hypotheses. And this is basically a generic way of adding arbitrary hypotheses in to the axiomatization of concurrent Kleene algebra, and getting automatically a sound semantics. and you don't get automatically completeness, but it does help to structure the completeness proofs, and so it is some help to prove completeness. And this is very useful because you can add extra structure on the alphabet with such hypotheses. So here we have this, in the alphabet we could have conjunctions, and those are commutative, so we could express this with hypotheses. We could also add some structure on traces. So here we add also the fact that two tests can be, two observations, sorry, can be merged together. But we could use it for other stuff and add other domain-specific assumptions. So this allows you also to treat your alphabet as some sort of the set of primitives of a domain-specific language, for instance. So we think this can be very useful beyond just Kleene algebra, a concurrent Kleene algebra with observations. So now we thought, okay, we couldn't use the test, so we added observations. So now we'll be able to do verification, right? So let's start with something fairly simple in the world of concurrent verification. Memory models, and especially weak memory models, no, not so simple actually, but are very concise examples of concurrent behavior that is realistic. So there is this, so people who try to check that hardware satisfy various kinds of properties, they use tests like these that are meant to check whether the hardware does what it's supposed to. And so this particular test works as follows. You have two registers, R0 and R1, both initialized to zero, and then you run two threads in parallel. One will put 1 in a shared variable x, and then put in R0 the contents of the shared variable y. The other thread does the converse. It first puts 1 in the shared variable y, and then puts the value of the shared variable x in the register R1. And something wrong happens if at the end of this execution, it is not the case that either R0 or R1 contains 1. Because, initially, yes, so if you want to prove this manually, intuitively, you start with one of these starts executing first. So say the first thread starts its execution, x contains 1, and then whatever happens, later on at some point, the second thread is going to execute R1 equals x, and so it's going to take the value 1. The problem is that in modern hardware, computers try to be clever, and they try to reorder instructions, but sometimes they do so only considering local dependencies, and you can get nasty situations like this. So we wanted to model this example in concurrent Kleene algebra with observations. So the first thing we did was see which kind of primitive, which kind of alphabet we need. So we need assignments for the actions, and then for the observations, we need to say that certain register, certain variable has a certain value. Right, so we use this as our atomic observations, maps from pairs of a variable and a value. Boolean formulas are sets of memory states. A Boolean formula will be interpreted as a set of memory states, so a set of functions from variable to values. And you can represent the semantics of an assignment by saying, for every possible state, if I execute the assignment v receives n, I get the same state except the value of v has changed to n. So x receives 1 is if you have just two variables and two values. Oh yeah, I'm missing one actually. But yeah, the semantics of x receives 1 is something like this. except this doesn't work actually, because if you have you want to execute x receives 1 and y receives 1 in parallel, and say they start from the same initial state. Both x and y are 0. If you execute the first one, at the end of the first thread, you're going to get the state x is 1, y is 0. At the end of the second thread, you're going to get x is 0 and y is 1. And those two states are incompatible. There's no neat canonical way of merging them again. So we need something else. And again, we need to find the guilty party. And here we blame the Boolean formulas. We blame the fact that the Boolean formula basically assumes a total knowledge of the world. When we go, yeah. Yes, and so to a better model for this kind of stuff in a concurrent world, instead of having memory states that are maps, total functions from variable to values, we consider partial functions from variable to values. And this is better intuitively in a concurrent setting, because it allows you to take into account the fact that in a concurrent setting, a thread only has a partial view of the memory of the general state of the system. It only knows the values of those variables it manipulated not too long ago, and it doesn't know what happens in other threads. And fortunately, there's already an algebra to deal with this, which we had to modify slightly, but not too much. It's called pseudo-complemented distributive lattices. And the idea is just to weaken the negation in such a way that the you weaken the negation somehow to get something that is a sort of epistemic negation. So for instance, the negation of V is n will be modeled as the set of all states such that V has a different value than n. So it's not only V doesn't have the value n, it's V doesn't have the value n because I've checked the value of V and it's not n. And with this model, we can adapt very slightly the semantics. It doesn't change much, actually. Just the definition of the interpretation of the negation changes slightly, but that's it. And then we get a new model that we call partially observable concurrent Kleene algebra, or POCA. And again, we have the same thing. Two programs are provably equal if and only if they have the same semantics. But there's still a problem to model, to represent what we want in here, because there's a tension between causality and compositionality. In this kind of frameworks, these are very compositional frameworks. So this means that the semantics of a program already contains all of its behavior in any possible context. So in particular, you need to allow the state to spontaneously change, the values of variable to spontaneously change, because in some other context, there might be some external concurrent thread that is going to come and modify the variable. And this is, of course, this is very nice because compositionality is nice, but it's also very inconvenient when we want to check that the value of the variable is 1 and not 0. So the solution is to explicitly close the system, to say at some point of the modeling activity, we say, okay, this is the system we want to consider, and we don't want to consider any outside interactions. And to do this, we defined a notion of causal Palmsets, which is a a formal way of saying Palmsets where there is a justification for every change of state. So whenever you have two states and they're different, and they're ordered, there must be some action in the middle that changes the state. And with this, we can correctly analyze the litmus test. And so the program I showed on the first slide of this this part can be written as this POCA term. So you can recognize here the precondition, the two threads in parallel, and then the post condition. And indeed, if you take the semantics of this guy, it does not contain any causal Palmsets. So this model does not fail, at least with this test, sequential consistency. Interestingly, you can change some axioms slightly and get a different answer. So you can fiddling with the axioms and the corresponding semantics, you can model different kinds of weak memory models. And in particular, you can model models where this fails, where you do break sequential consistency. And now I'm going to present something slightly different, but very related. So another useful thing in concurrency theory is mutual exclusions. This is a case where often you do want to check that indeed there's no interference between two critical sections. So I use this very simple example. You have a shared counter, and you have two threads in parallel that try to increment the counter. And they do so by loading the value to a local variable, incrementing that local variable, and then writing the result to the shared counter. And this can be represented by this simple program or this very simple Palmset as well. Now, if I look at all the possible Palmsets that are smaller than this one, I get, for instance, this one, where everything happens nicely. I do read, compute, write, and then read, compute, write, and the counter has been incremented by 2, and I'm very happy. But I can also do this. Execute both reads first, then both computes, and then both writes. And so the effect is that the counter has been incremented by 1 and not by 2, and then I'm not happy. So how can I correct this? Well, in the program, what you would do in a reasonable programming language is add some sort of atomic construct, or maybe it's add some sort of atomic construct, and that will do the trick. That will prevent any interleaving of one thread inside the other. So the idea is to do the same with Palmsets by adding boxes around certain sets of events, protecting those sets of events from outside interference. So if I add these boxes here, protecting each thread, then I can see that the first interleaving is fine because I can reproduce those two boxes on this interleaving, and it works. And indeed, this was an example we wanted to keep. But the second one is rejected because there's no way of properly drawing those boxes on the second Palmset. So how do you define formally Palmset with boxes? Well, you take a Palmset and you say it also has boxes. So you add to the tuple a set of non-empty sets of events. So here I have two boxes which are nested one inside the other. And you can very easily define subsumption between such structures. So it's the same as before. It's P is subsumed by Q if there is a map from the events of Q to the event of P, that preserve labels, preserve the order, and now that it has to preserve boxes as well. But we allow the small Palmset to have more boxes. The idea being that boxes restrict behavior. They're meant to protect, so when you add a box, you have less behavior. But you still have those behavior. By dropping the box, you don't get more behaviors, something like this. We axiomatize this without the Kleene star because it was easier. And so we had a small completeness result that was fully developed in Coq to show that indeed adding these axioms, so the fact that boxing twice is the same as boxing just once. Boxing the empty Palmset is the empty Palmset. Boxing 0 is 0. Boxes commute with sums, and box E is smaller than E. And we have this correspondence between the axioms and the semantics. Now can we do mutual exclusion? Well, we can write the program that we wanted. So it's the syntax is very similar to what you wrote here, except that it's linear instead of being two-dimensional, but you have, this dot is a sequential product, you have the parallel product, and you have boxes around parts of the term. So what does it mean to break mutual exclusion? If we want to verify this, we need to express the property. Well, one way of looking at it is saying that breaking mutual exclusion is the same as having an execution where both reads happen before both writes. Right? So you have what you do want is that when at least one of the writes happens before the other read, so that the counter has been incremented twice. The problem is that saying there is no execution with this pattern is not expressible in an inequational form. Yeah. For instance, you can't write it as the program is smaller than some specification, because the language of all Palmsets that satisfy that have this pattern, or all Palmsets that do not have this pattern, is not expressible, even with unbounded parallelism. There's no way to get this one. So what can we do? Well, we need a more expressive specification language. We're fairly happy with the programming language, but the specification language is not expressive enough for some fairly basic stuff that we want to represent. So we added a new, we introduced a new specification language, which we called Palmset Logic, even though we learned afterward that there was already a Palmset Logic, which is very different, introduced by Christian Rétoré and Alain Lecomte in the 90s. So this one is inspired by separation logic. So you have Boolean connectives. You also have two new conjunctions that are like the separating conjunction of separation logic. So a Palmset satisfies this triangle one is called then. So P satisfies phi then psi, phi then psi, if P is larger than some Palmset P1, some Palmset P1 composed with P2. P1 satisfies phi, P2 satisfies psi. Similarly, this star is the same thing, but with a parallel composition. The box is the same thing with the boxing operator. So P satisfies box phi if P is larger than some Palmset box Q, and Q satisfies phi. And we have also another construct, the context operator. So P satisfies context phi if there are some Palmsets P prime and Q, so that P is larger than P prime. P prime contains Q, and by contain, this is the idea of an induced substructure. So you keep some events and the structure around those events, and Q satisfies phi. And we have actually we have a number of variations around this this logic. We can tweak some things slightly, but in particular we have this theorem that this logic is adequate. That a Palmset P subsumes a Palmset Q if and only if every formula satisfied by P is also satisfied by Q. And now we can handle mutual exclusion because we were able to write the program that we wanted. And now we can express the fact that the program satisfies the program violates mutual exclusion using this formula that in a context, there are events read X and in parallel read Y, followed by write X and in parallel write Y. And so we can check, and this is all finite, so we can actually check algorithmically that this program actually does not break mutual exclusion, it does enforce mutual exclusion. And now I'm going to conclude briefly. So one thing that I'm working on right now is a more generic way of doing all those modifications and extensions and adaptations of various algebraic formalism. So in particular, there was this idea of algebra with hypotheses. So Duman, Kuperbeck, Pous, and Pradic introduced Kleene algebra with hypotheses. And then we took exactly the same definitions, just replacing Kleene algebra with concurrent Kleene algebra to do concurrent Kleene algebra with hypotheses. And the definitions are remarkably similar. The proofs follow exactly the same pattern. And yet we could not reuse any lemma or even definition from them. We had to paraphrase everything they did, redo all the proofs, and get the same results. And this is a bit frustrating because now I want to do the same thing with boxes, and we would have to go through the motions of doing exactly the same thing again. And so there should be a better way, and I'm fairly convinced that there is a better way, but it's not ready yet. Another aspect that is interesting is this Palmset logic I touched on in the last part of the talk. Traditional approaches to program logic rely on states. Usually you have some sort of crypt key structure. You have the interpretation of the logic is formulated in one way or the other in terms of being in some state, performing an action and going to another state. And the logic mostly talks about those states and the reachability conditions between those. But here, our logic, in our logic, there's no clear notion of state. I use the word state at times because it was a convenient analogy for these valuations of variable to values, but there's no clear notion of state, and indeed the logic is less does not lend itself easily to bisimulation-like approaches, but works mostly by considering behavior. The basic notion is traces and behaviors, and this actually opens, I think, a lot of questions about what are the kind of properties that we can capture with this, that we want to capture. It's trying to write specification in this setting. You realize that it's a bit counterintuitive, and it's quite different than what we're used to. Other extensions that I'm keen on the boxes side. I'd like to add this axiom about merging boxes. So the idea is that the box is supposed to protect the behavior somehow. And if you have two boxes that are one after the other, you can actually achieve the same protection by just putting a single box around them, because that way nobody from the outside can be interleaved in between. That's fine, but you can't have any event from the blue one that gets interleaved with the red one, because they're already ordered, so there's no possible interference between them. And I'm fairly convinced that just adding this axiom and something along those lines in the semantics would get, again, correspondence between the axiomatic presentation and semantic presentation. Another thing that that does work, this has been written down in the POCA setting. We had this pseudo-complemented distributive lattice of partial functions. But actually, we can be much more general than that and consider an arbitrary finite set of atomic observations, and then some coherence relation between them, which in the case of this partial memory state, we would use this coherence relation to say it's not coherent that V has both the value 1 and the value 0. So you can use this coherence relation to say which are the observations that can be made of the same state and which are the observations that cannot. And this gives an algebra that is remarkably similar to coherent spaces, if you know a bit about models of linear logic. And yeah, and it was just as well as those algebra of partial memory states, or the Boolean algebra that we used before. It's completely compatible with this approach. And also something that I'm keen on is adding data to those things and considering the nominal versions of those. And we're actually working on this with some colleagues these days. And that's what I wanted to talk about. Thank you very much.
Thank you for your very interesting talk. And does anybody have questions?
Hi, Paul. Thank you very much for the talk. It was very interesting. I have a question related to restrictions of this approach. Am I right that Kleene algebras, I mean, like some kind of extension of Kleene algebra, they still they don't support function calls, or do they?
Not quite. No. It's I think they operate at a lower level than this.
Mm-hmm. Because I mean I would expect, since like Kleene algebras are that close related to regular expressions, I would expect that to have support for functions you would need something like context free, like, right?
Yes. Yeah. You need something like this.
Thanks.
I mean, I think it's more related to like general recursion. Like you can have some like what's called like tail recursion. You can model it with Kleene star, right? But for general recursion, you need a fixed point operator.
Yeah, and also if you, I mean, yeah, this is very basic, but if you you can of course define systems of Kleene algebra terms that refer to each other, and if you're careful about who is allowed to refer to who, you can still compile this to Kleene algebra expressions. But of course, the complexity changes dramatically because you can be much more concise and in your syntax.
Thanks.
More questions? Actually, I have one. You mentioned that some of these logics is decidable and space complete. Yes.
Yes.
And what about the how these extensions, adding boxes, etc., changes this classification?
So, so I'm not completely sure is the honest answer, because I mean we know they're all decidable because all the proofs are constructive, and but they are proofs, not algorithms. So if you take the algorithm you get from the proof, it's horrendous in terms of complexity, and we haven't tried to apply tried seriously to apply the more sophisticated techniques. I would expect that the extensions with observations will remain space complete, because first, this is what happens for Kleene algebra and Kleene algebra with test. Adding the test does not change the complexity class, and for the boxes, I would think as well it remain space complete. It's a very big class, so you can be pretty messy and stay within X space, and these do not change dramatically the overall behavior of the. I mean, it's more a matter of dismissing some behavior that you don't like anymore, and so it shouldn't make the problem much harder, but would need to be checked, right?
Thank you. Any more questions?
Yeah, I have a couple of questions. So first of all, thank you for this great talk. The first question is about, you mentioned briefly weak memory models, and I guess it was the slide with this litmus test.
Mm-hmm.
Yeah, and you mentioned that you showed us that we can take like the semantics of key, the program, the litmus test, and we take the intersection with like some set of, you called causal Palmsets. So am I right that by changing this set of causal Palmset to some other set, you can get another memory model? So basically this causal Palmsets model, the memory model that you consider, right?
So it's not how we did it. It's conceivable that it would work like this, but what we did instead is add some axioms, so change the semantics of E rather than the notion of causal Palmsets.
Mm-hmm.
Changing the whether you're allowed to how you're allowed to merge states, or can they adding some commutativity, that sort of thing.
Okay. Yes.
Because to the litmus test, like in reality, it would fail when the compiler exchanges two instructions. So to make it fail meaningfully in this algebra, you need to be able to exchange the order of certain actions.
Mm-hmm.
And this you can't do by restricting, because if you don't change the axioms, you will never get this behavior. By just taking an intersection, you won't be able to add this behavior to the.
Okay, I see. Thank you. So do you then consider some commutations between certain actions, or?
Yes. So I don't remember exactly how the definition, but I think it's in the paper. If you look at the paper, we will discuss this briefly at the end. But we do write the axiom that you need to add.
Yeah, okay, thank you. Yeah, by the way, small commentary on this. I think that in general you might need not the commutations but semi-commutations. So there was some work recently by Hendrik Marat and Armautsu, I guess. They were trying to do something similar, but they consider this how do you call this model? But so basically they consider not the commutations between actions, but semi-commutations, which act like, I don't know, some kind of rewrite rules. Because like in rewrites, like in these weak memory models, there are some cases when you don't have like two-side commutations, but like only one side. Like you can change the order only one way, but not the other.
Yes, yes. Okay, yeah.
Yeah, thank you. And another, not a question, but a commentary. So you mentioned that this notion of Palmset subsumptions. So one can see this as like the relation between the specification and the implementation.
Yeah.
And this is a very nice idea that I also like had the same idea in mind. And I know how you are you working on something in this direction. Like for example, you can have you can basically do something like trying to prove that some concurrent data structure is correct with respect to its implementation by showing this homomorphism between two Palmset languages.
Yeah, this is. I mean, generally for this kind of frameworks, this is how you should reason about the ordering, because the semantics of the expression is its set of behaviors. So an expression is smaller than another one if all the behaviors of the small one are behaviors of the big one. And naturally, this, to me, the natural conclusion is that you should interpret this as saying that the big one is the set of legal behaviors, and the small one, the program, should make sure that all of its behaviors are legal.
Mm-hmm. Yeah, thank you.
More questions? No? Well, if there is no questions, thank you very much once again for your wonderful presentation.
Thank you for listening.
Thank you.
Thank you.
Thank you.
Goodbye.
Bye.